Hi, my name's Chris Esposo, and this is my partner Val to C2. We are here working on our project. We wanted to do something a little different from everyone else, in that we actually have a project that I actually worked on when I was at graduate school at Georgia Tech. And I'd like to acknowledge my project teammates who were co-partners in developing this model at NetLogo. Was myself, David Chi, Dylan Garrett, and Eric Miao, um, all of which I think have graduated at this point. And so basically, I took this AI planning course because I have been dealing with a lot of these sorts of agent planning and agent models, both in my coursework and as well as in my professional work now. And so I thought it was a really cool class, and I got a lot of it. And Val, also my partner, he did as well. So what we're doing is we're analyzing a model we built to give you a real quick explanation that is explaining that's trying to model the Battle of the Marne. And for those of you who don't have maybe a good grasp of history or don't remember it very quickly, the Battle of the Marne, in particular, the Miracle of the Marne, was one of the earliest battles in the First World War between the Germans and the French. And so the problem statement here is there was something called the Miracle of the Marne, and it was basically that the French were able to deploy, as historians say, a group of taxis to the front from Paris just in time. And the taxis served as a very good vector of transportation for the soldiers that allowed them to effectively deploy their soldiers to the key locations in the front, that allowed them to prevail against the Germans in the First World War in that particular battle. And so my project teammates, about a year ago, we developed this model. I think you'll agree it's kind of cool. We load up the script here, and so what you're going to see on screen is this is the front right here. You'll see that. Um, this blue represents deposit points for the French, the Allies, and these red boxes represent deposit points for the Germans, the Central Powers in this case. We did it, as you note, right here. We have this huge transportation network modeled right here for the Allies and not much for the Germans, and that was just because of time. We were planning actually a much more larger model and more complicated one, but just doing this one was very difficult in terms of our constraints. What you also see here is there are these train networks that we modeled, and so this is from historical maps. These are actually where the trains were able to go, and where the French would have had access to them to also deploy their troops. And so it's sort of like a multimodal problem. You have access, you can send troops through trains, you can send them through taxis, and then you can just put them through foot. Given those options and given the conditions of the front, what's the best vector to go ahead and do that? Also note these circles right here. These circles are rally points where troops can be deposited. And in our code, what the circles also do is they send sort of signals cascading back. So this circle to this, depending on the condition on the front here, this circle will send information back here saying, "Oh, I'm losing here in this part of the front. So send information back to this circle, which will send information back to that circle, which sends it back all the way back to the source in Paris, which then gets the command to send more troops through one of these vectors, either trains, taxis if they have access, or through the foot. So that's the model explanation. I think everything else is you can figure it out. So I'm just going to go ahead and run this. And then what we're going to do is we're going to talk about how we can go ahead and extend this model. We've been wanting to do that. And it's one of the reasons why we took this course was to take these sorts of problems and sort of extend them beyond what we had originally did, because we didn't know about AI planning when we first developed this. So I'll go ahead and press go, and you can see right here. I'm not sure if I got the correct parameterization, but the French are kicking the Germans behind right now. But oh, they got a command right here. These icons represent trains. I have to again thank David and Dylan for that. They they had a nice, very nice icon set up. And these blue icons here, these are taxis. And what you see here is you see these zeros and ones. They show basically they signal that certain nodes are commanding. They're sending information back to the source, saying, "Hey, I need these guys. I need them more here." And you can see that right here, the front is weakening, and the taxis have diverted. They were one group here, and then they partitioned into two groups, and they are being sent to the front. And as the trains go in and they go to deposit points, they deposit their soldiers, which are these little green men, and the trains now become yellow, and which means that they are empty, and they can go back to Paris to deploy more soldiers. Um, so that's basically it. And now you're gonna see. Let me just speed this up a little bit. There we go. You'll see that the taxis have now also starting to deposit right here to the front, where the allies are weakest, and hopefully that's going to prevent the front from breaking. Um, you can see here statistics on the current the order of battle, how many soldiers, how many total French and German casualties there are currently. Uh, there's all kinds of statistics we actually had developed. Oh, they got another command line right here from the French, so they're deployed more soldiers via train. Um, and yeah, oh, one thing I didn't explain was that there was a lot of historical contention um, in the literature, base evidently on were the taxis actually relevant to prevail during that battle. And this is why we actually allowed for the model to change initial conditions and how many taxis the allies or the French had access to, and how many trains they had access to, so that we could do historical analysis, counterfactual analysis on what scenarios, what different scenarios, what would have occurred. So that's sort of a really quick rundown on the model. And so where this is relevant is that actually in there's a breed of modern military simulations, similar to actually real-time strategy games that were discussed in the course, that use all kinds of sophisticated computing techniques. These are very large system of system simulations. They have their own what's called a military query language that allow you to program the simulation and interface with it to build, these sorts of scenario builders that allow military planners to figure out, where they should deploy troops and logistics and things of that nature. This particular model was a cross between a logistics chain, supply chain model and an agent model. But there's all kinds of different models that the military use. They use, for instance, system dynamic models as one of them. They use, basic regression, partial differential equation models as well. But this one I thought was graphically interesting, which is why we went ahead and did it. So that's a big explanation. That's a quick explanation of our model that my colleagues from Georgia Tech, again, I'd just like to say, as myself, David Chi, uh, Dylan Garrett, and Eric Miao, again, really bang up job on the project. We did very well. Um, and so now the question is how can we utilize the learning from AI planning to extend the model, and maybe create something even better. And this is where I was excited to bring my other colleague here, Val Tositu, who's studying simulations also, and so he had some ideas in how we can go ahead and extend this, and I just let him talk about it, and maybe we can sort of maybe if some of you guys are interested, maybe we could all collaborate together as well.